Okay, we are moving on to Unit 8. Unit 8, Inferences of Categorical Data with chi-squareds. Okay, so there are three different chi-squared tests that we will be looking at in this section, or in this unit. The first one that we are looking at is known as the goodness of fit, or the GOF test. Okay, so these are the three different ones that we have. Each section is going to go over one of them, and they all use the same process, but they don't use the same. They don't find the same thing. Okay, so they all find something different, but it's essentially the same formula that you use over and over and over again. Okay, so we're looking at the first one, the chi-squared goodness of fit test. Okay, so the goodness of fit test basically asks, does this distribution fit? So you'll be given a set of data and you'll be told, is this a uniform distribution? So are they all the same? Is it a normal distribution? Does it have that nice bell curve? Or is it skewed one way or another? Okay, it might also have all the numbers are a certain percentage, 25%, 30%, 20%, 10%, so on. Okay, so it could be specific percentages that you can do as well. So goodness of fit test is basically asking, does it fit this distribution? Yes or no. Okay. Now, when we're doing any type of chi-squared test, we are looking at the observed values that we got compared to the expected values. Okay. And we want to know the expected values would be something that's like, oh, hey, it's supposed to be uniform, so they all should be the same. So they all should be, 30, 30, 30, 30 across the board. And then you look at the actual numbers, which very rarely will it ever fit that. Okay. The bigger difference between the expected and the observed, the more likely that you're going to reject it because it's less likely to fit that distribution that was stated. Okay. So the larger the differences between them, the more likely it is rejected. So this is just, again, trying to find, does it fit a certain distribution? So a chi-squared test, again, compares the observed values from the expected values. And to find the chi-squared, what you are going to do is you're going to take the observed value, subtract it from the expected value, square that number, and then divide that by whatever the expected value was. You will do that with every single category that you have in an example. Once you have that, you would add them all up, and when you add them all up, you get your chi-squared value. Okay? And a large chi-squared value means failure, or means rejection. Okay? Now the shape of the distribution. So a chi-squared distribution is not like a normal distribution. It is a right skewed, because you see the tail, distribution. And the main reason for that is because you do not have negative values. Because you are squaring the differences, it turns every number positive, and then you're just adding them all up. So you always end up with a positive number. If you get a 0, that means it's a perfect fit. If you get an infinity, that means it's a terrible fit. It also uses a degree of freedom, because the more categories you have, the bigger that tail is going to be. Because if you only had 2 categories, okay, that means you're only comparing 2. So that means your chi-squared value is going to be fairly small. But if you're looking at a larger group of categories, let's say 100 categories, you'd want to be able to have some fluctuation with those, okay? And not just, oh, well, this one is, if they were the same number, if let's say a chi-squared of 2 leads to rejection, if you had 100 categories, it's going to be a lot easier for it to get a rejection, okay? Because you have to add up 100 numbers, okay? So it does use degree of freedom, okay? And degree of freedom is essentially the number of categories minus 1, okay? So how many groups you have minus 1. So again, it uses a p-value, okay? And it's just like with our other ones, it's asking for what's the probability that this is a chance variation. And so if your p-value, if the calculated value is less than the p-value that was given, then you are going to reject it. Okay, so that's what we're kind of looking at, is seeing, does it fall into this chi-value? And so when you add them up, you get a number. So in this example, the chi-squared was 10.180. So any number that was greater than that falls into that p-value, and your p-value would be smaller, leading you to rejecting the null hypothesis. Okay, and this is for a degree of freedom of 5. Okay, so for conditions of a chi-squared test of goodness of fit. Now, your random, independent, and normal. When you're dealing with a chi-squared goodness of fit, okay, random sampling, 10%. And then the last one is kind of new. You need each category to be at least 5 for its expected value. Okay, so this is important that it is the expected, not observed. So if the expected values are all in every single category is 5 or more, you can continue. Now, that is the only one that is important, okay, with this. When you are doing your 4-step process, you do not have to name off the random and independent when you're doing a chi-squared GOF test. You just need to show the normal. Show that it is all the expecteds are greater than 5, which is when you create your expected table, okay? And we will talk about ways of making expected tables and different things. Okay, so goodness of fit test, step 1, again, is to state off your kind of what you're trying to find and your hypotheses. So there's 2 ways of doing your hypotheses. One is to say your null hypothesis is that a specified distribution of the categorical variable is correct. Boom. Now, if you want to be more descriptive, you can. It's a normal distribution, a uniform distribution, etc., etc. The alternative hypothesis that the specified distribution of the categorical variable is not correct. So that's your alternative, that it is not the distribution that was stated. Okay, this is again an example. You can reword it a little bit, but you want to talk about a specific distribution, categorical variable. The null is correct, the alternative is incorrect. Or if you don't want to do that, you can state what the proportion is for each category. Now, if you have 13 categories, that could be very difficult to write all those out. Okay, and then the alternative of this is that one of them is not correct. But if you only have like 3, you could go, well, this one is 20%, 30%, 50%, boom, done. And then your alternative is that at least one of those is incorrect. Okay, so just one is incorrect. Will reject the null hypothesis. Okay, because again, we want it to match up the distribution that was given. All right, so before you do the test, okay, you need to look at the expected counts. Okay, so again, the expected counts are the important parts. Okay, and make sure you are doing the counts of them and not the proportions of them. So if it's supposed to be 20% and you have only 10, that means that the expected value should be 2. Okay, it's not 20%. So when you find your expecteds, find it in the raw numbers, not the percentages. Okay, so that's how it would be. And again, when you check for your large count condition, which is your normal condition, make sure you're looking at the expected values and not the observed values. Okay, so just some warning. So make sure you use counts, not proportions, when you're doing these calculations, and make sure you're looking at the expected counts when you're looking for the large count conditions. All right, so let's do an example. Okay, with this. So this research is dealing with looking at soccer players and seeing if their certain month in which they were born, it's more likely that they can be successful in soccer. And if when they were born didn't matter, then all their birthdays should be approximately the same. Okay, so the distribution should be equal across all. And so we have, they took the 1990 soccer players. This is a real study, and there is reasonings behind it for it, which kind of depends on how your school year goes, because you could be more mature or less mature, and kind of the age cutoffs. But they wanted to see if it was an evenly distribution, you have a 0.05 level of significance, and then you have these numbers. Okay, so you have 150, 138, 140, and 100. Those are your observed values. Now, first thing you'd want to do is find your expected values. You want to state which one it is. Since this is looking at a distribution, seeing if a distribution is correct or not. What you would say is that under your state section, you are going to say it's a chi-squared goodness of fit, or GOF test, okay? And then your null hypothesis is that the birthdays of soccer players are evenly distributed across the quarters, and the alternative is that they are not evenly distributed. And see, the alternative is not saying it's another distribution, it is just saying it is not the distribution that was stated. And the one that they were saying is that it was even. Now, since it is uniform across it, you would add up all the people that were asked. There was 528 soccer players that were asked. And so you would add all those up, 528, multiply it by how many categories there are. There was 4 categories, so, or you could say divide it by the number of categories there are. There are 4, so there should be about 132 in each. And those are your expected counts. So under your plan, this is all you really need to do. You just have to show that the expected counts are all less than 5, or more than 5, my mistake, are all more than 5. And that's all you need. You don't need to do a random, you don't need to do an independent, okay? You just need a normal, which is the large counts. So you got to find the expected values. Now, if they tell you certain percentages, then you take the grand total and multiply it by the percentages and everything. If it's a normal distribution, hopefully it's easier than that. After that, you have to do your do. Okay, so to do your do, what you're going to do is do your calculations. So you take the observed value. So in the first quarter, there was 150. The expected was 132, so you subtract those, square them, and then divide it by 132. And then you go into the next one, 138 minus 132 squared all over 132, and then 140, so on and so forth. And you do it for every single category. Now, I know what you're thinking, this is going to take forever if I have about 8 categories, and that's true, but your calculator can make this a lot quicker and easier, and we'll talk about how to do those, how to do it on the calculator for you, okay? So don't worry about that. After you calculate all this and you add them all up, you get a chi-squared of 10.96, or 10.97, I guess, rounded, 10.97. The degree of freedom is 3, and the p-value, which you get from your calculator, was 0.012. And since that p-value of 0.012 is less than the alpha that was given, that means that you would reject the null hypothesis. You do have convincing evidence that the birthdays are not evenly distributed across the quarters. Okay, and if you look at the main difference, if you did each one of those calculations, your chi-squareds, the first quarter, the chi-squared you got was 2.45, second one was 0.27, next one was 0.48, and the last one was 7.7. So you look at that and you see the biggest one that had the largest effect was that fourth quarter one, because it was the farthest away from what was the expected value. And so that is the one that has the largest effect on it, has the largest number. Okay, conclude. Fairly simple, fairly easy. All right, so let's do on the calculator. Okay, on the calculator, if you go to, what you would do is you would type in all of your observed counts into L1, all your expecteds into L2. Okay, so you have all those. You go to stat, go over test, D, chi-squared GOF test, observed, make sure it's L1, expected L2, and then you have to state what's your degree of freedom, okay, which in this case is 3 because there was 4 categories. 4 minus 1 is 3. After you push enter on that, okay, it comes up with this. It tells you what your chi-squared value is, which would be that 10.97 number. It tells you what your p was, which was 0.012. Okay, this is going to be the easiest way to get your p-value. If you're not going to find your p-value, then you have to compare the chi-squared to the value that was given with the chi-squared. So you have to use table, I believe it's table C. DF, the degree of freedom, and then also the contributions, which is the CNTRB. And it tells you what each chi-squared value was. So from there you can see, oh, this was the one that was least common, or this was the one that had the biggest difference. This was the one that had the smallest one. So from that row you can see the individual calculations of each one. Okay, and that's what the contribution does. Now, some of these, whenever you do reject, you will be asked to do a follow-up on it. And from here, it's basically which one has the largest change, which is, in this case, the fourth quarter, which makes sense because usually kids that are in the fourth quarter of, let's say the age cutoff was in August, where the beginning first quarter of this one was, they're younger than all the other ones. But that's just how it is. Okay, so it's more likely for them to advance and everything. Okay, so that's the chi-squared goodness of fit test, which means you have to look at the distribution, see if the distribution fits or not. All right, we will be moving on to section 2, which is the chi-squared test of homogeneity.